Okay, so chapter 10 is all about acids and bases. We've obviously talked about acid and base reactions before. We've dealt with acids and bases in a very simplistic way, but now we're going to explore them in a lot more detail. So first of all, acid and base activity is defined entirely in the context of an aqueous solution. So we'll see later today about how water is just a central player in acid-base reactions. An acid isn't really an acid in many ways until it's dissolved in water. And an acid will produce, when it dissolves in water, it will produce hydronium ions, H3O+. And a base, when it dissolves in water, will produce hydroxide ions. And these two things are related to each other. Again, we'll see that quantitatively, the relationship between H3O+ and OH- a little bit later as well. But acids and bases are all the diverse acids that you have are going to have the same effect in the end. They're going to produce hydronium in solution. And all the different bases that you can find in the chemical stockroom are going to have the same effect. They're going to produce OH- in aqueous solution. So you can see here that the concentration of H3O+ can range pretty wildly. You know, things that are very basic, like 1 molar sodium hydroxide, will have an H3O+ concentration of 10 to the negative 14th. Whereas things that are really acidic, like 1 molar hydrochloric acid, will have an H3O+ concentration of 1 molar. So that's a range of 14 orders of magnitude. Pure water is going to have 10 to the negative 7th molar concentration in both H3O+ and OH-. And you can see on this figure a range of different common substances. Human blood is slightly on the basic side. Milk is slightly acidic. Coffee is there at a H3O+ concentration of maybe 10 to the negative 5th. Tomatoes even more. Vinegar and lemon juice and stomach acid are on the acidic end, and then things like milk of magnesia or household ammonia are more basic. Baking soda is pretty mildly basic. So there's, give me a sec, let me get to the next figure. Acids and bases, because of the sorts of reactions that acids and bases do, they are pretty ubiquitous in household products around us. Vinegar, for example, is really an aqueous solution of acetic acid. Nitric acid is used in a lot of chemical industry for producing fertilizers and ammonia and explosives. And on the other side, on the basic side, we'll use bases in cleaning and fertilizing. Anyway, this table is in your textbook. If you are interested, you can kind of scrutinize it and see all of the different applications that acids and bases have in our everyday life. So let me make this figure go away for a sec. Okay, so let's get a little bit more sophisticated about how we define acids and bases. There are at least 3 different common definitions that you'll use in different contexts. But what we will use is the Bronsted-Lowry definition. Bronsted-Lowry acids and bases are defined in terms of protons. So H+ is really just a proton. Remember, a hydrogen atom is a proton with an electron. Well, when you turn it into a cation, it loses the electron, and so this is a proton. H+ is a proton. And so a Bronsted-Lowry acid oops, forgot the C. An acid is a proton donor. That means in a chemical reaction, it's going to donate a proton to its reaction partner. So let's consider HCl plus H2O. I have hydrochloric acid reacting with water. That's going to form H3O plus and Cl minus. So let's see, is that on screen? Yeah, just barely. So if we inspect this reaction, we'll see that what happens is that an H plus goes from the hydrochloric acid and attaches itself to the water. And so what that means is that HCl is donating a proton to its reaction partner, and that makes HCl an acid. So a Bronsted Lowry base, and I should have written everything about a foot to the left, so that's what I'll do over here for the base. So a base is a proton acceptor. So a base will accept a proton from its reaction partner. We can look at ammonia, NH3 aqueous, reacting with water, plus H2O liquid. What's that going to produce? We'll have NH4 plus aqueous plus OH minus aqueous. And so if you inspect this, you see what has changed is that the water has provided a proton, an H plus, to the ammonia. So it has one more hydrogen, and now it has the positive charge. The hydrogen accepted that proton, and so it is a base. And you cannot have an acid-base reaction without both an acid and a base. So now we can go revisit this hydrochloric acid with water reaction, and we see that hydrochloric acid donated the H plus and water accepted it. And so that means that water is acting as a base in this reaction. And here we see that the ammonia is accepting a proton, but who donated that proton? The water did. And so in this case, water is acting as an acid. So we'll talk a little bit more about water later, but I just want to point out that water can act as either a base or an acid depending on the context of its reaction partner. And it's the fact that water is sort of perfectly balanced between acids and bases that makes water behave in the way that it does. That's what makes water be what we define as neutral. This definition sort of matches what we said earlier. The acid did indeed produce H3O plus, and the base did indeed produce OH minus. But this definition of acid as a proton donor and base as a proton acceptor is more versatile and more general than just talking about hydronium and hydroxide. For example, what if I react hydrochloric acid with ammonia? So if I have HCl aqueous plus NH3 aqueous, that is going to produce NH4 plus aqueous plus Cl minus aqueous. So you'll notice this reaction didn't produce any hydroxide ion or any hydronium ion, but it is still an acid-base reaction because we still have an H plus being donated by the hydrochloric acid being accepted by the ammonia, and so we still have an acid and we have a base. So the Bronsted-Lowry definition being centered on the exchange of a proton is more versatile. It's a much better definition. So we have some acids which we call multiprotic. So if I have H2SO4 plus CO3 2 minus, then the product of this reaction is going to be H2CO3 plus SO4 2 minus. And so you'll notice that the sulfuric acid, H2SO4, has donated not one but 2 protons to the carbonate ion. And so this is called a diprotic acid. So it's able to donate 2 protons. You can have a triprotic acid like H3PO4. It's got 3 hydrogens there, and it's capable of donating all 3 of them in a reaction. So generally we can refer to these as multiprotic. Multiprotic acids. There are a number of diprotic acids, some triprotic acids, and even some tetraprotic acids. When you have a multiprotic acid, it doesn't have to donate both of its hydrogens at the same time. It depends on its reaction partner and how readily that reaction partner will receive hydrogens. So you could have H3PO4 at first donate just 1 proton. Depending on who its reaction partner is, maybe it will end up being H2PO4 minus. Or maybe the H2PO4 will donate another hydrogen, and we end up with HPO4 2 minus. And then that HPO4 2 minus might further donate its last proton, H plus PO4 3 minus. And so something like phosphoric acid, it can donate just 1 proton or 2 protons or 3 protons, depending on the context of its reaction. I'm going to go ahead and erase Bronsted-Lowry here. Okay, so let's look at an acid-base reaction that will reach an equilibrium. Something like acetic acid plus ammonia. This is going to reach equilibrium, and what you'll have is acetate ion plus ammonium ion. And if we look at this, it's clear that the acetic acid is donating its H plus to the ammonia. That makes acetic acid an acid and ammonia a base. But because this is an equilibrium reaction, we can also look at the reverse process. When we start with ammonium and acetate and generate acetic acid and ammonia. Well, what's happening here is that the ammonium is donating an H plus to the acetate ion, and that makes this an acid. And the acetate ion is accepting that proton. That makes acetate a base. And so every acid-base reaction is going to have acids and bases as the reactants, and then also an acid and a base as the products. We can sort of link these two. Acetic acid and acetate are, they differ only by a proton, right? Acetate is what acetic acid becomes after it donates its proton. And so we call these two a conjugate pair. Acetate is the conjugate base to acetic acid, and acetic acid is the conjugate acid to acetate ion. And then likewise, ammonia and ammonium are linked. They differ only in one H+. So NH3, when you add H+, becomes NH4+. NH4+, when you remove H+, it becomes NH3. And so they are also a conjugate pair. In other words, ammonia is the conjugate base to ammonium, and ammonium is the conjugate acid to ammonia. And so conjugate pairs are going to have a relationship to each other that we'll cover in the next video. But it's going to be very important for you to look at an acid-base reaction and identify what is the acid and the base on the reactant side, what is the acid and the base on the product side, and then which pairs are linked. So you'll have two different types of pairs. You'll have reaction partners. So acetic acid and ammonia, they are reaction partners. They're the two different chemicals that react together. And then over here, I suppose you could say that ammonium and acetate are reaction partners. And reaction partners don't necessarily have any relationship to each other. I could pick any acid and I could react it with any base. They don't have to have similar chemical formulas or similar strengths or anything. But conjugate pairs are special. They'll have nearly identical chemical formulas, differing only by an H+. And we'll see in a moment that they're related in their strengths as well. So I think we'll stop this video here and make another one in a moment.